Today I'm going to talk to you about our recent efforts in porting over a code that we've been developing for quite some time now to do hybrid density functional theory in the condensed phase. I guess at the end of the day with the focus on being able to do ab initio molecular dynamics. Just to give a little brief overview and a little bit of background, if one is interested in sort of unraveling the microscopic details of fundamental systems and processes of importance throughout any field of science, whether it's biology, chemistry, physics, or material science, one has to choose what method to use, right? And in some sense, there's an entire hierarchy or a survey of computational approaches that you can choose. And again, it's always a balance between accuracy on one hand and computational cost on the other as to what you should choose for your system of interest or problem of choice. On one end, we have quantum mechanics, and this is the area that we're going to focus on. There you're solving, or approximately solving, the Schrodinger equation, in this case the time-independent Schrodinger equation. However, this is really expensive, as we all know, right? So you're getting the higher accuracy end, but it's really expensive, so you have a tremendous need for computational resources. And you wind up being able to treat, sort of at a very, very high level, small molecules. Here I have one of our favorite molecules as scientists, caffeine, right? However, if you go to sort of the other end of the spectrum, right, you see again, as we get to sort of semi-empirical methods, we're gonna sacrifice a little bit on the accuracy or the transferability or the reliability. But we can start treating bigger molecules, like here some strands of DNA. If we move to the sort of classical molecular mechanics or classical force fields, you could treat much bigger systems. I have here a protein named ubiquitin, right? However, as we get to this end, you require the formation of an energy expression and a force evaluation that can be done in a very, very, very quick time, right? So you need analytical closed form expressions for the energy and forces. And of course, in order to do that, you probably should parameterize them on some quantum mechanical model system, so you really need empirical parameters on this side. So as I mentioned, we're going to focus today on methods in quantum mechanics, in particular, the hierarchy of density functional theory. I'm going to give 2 slides on the background of density functional theory for those of you that are not as familiar with it. I think this is just 1 or 2 take-home messages. The first thing is that density functional theory provides an alternative solution to the Schrodinger equation, right? Now, the Schrodinger equation is quite simple. Here's the time-independent Schrodinger equation. H psi equals E psi. H is your Hamiltonian operator. Now, again, I would argue that you can explain the Hamiltonian, right, which is a quite simple object, to anyone in the street, right? Someone that's not an expert in chemistry or physics or material science. Why? Well, you have a kinetic energy term, your electrons are moving, and then after that, it's all just basic, plus likes minus, minus doesn't like minus, and plus doesn't like plus, right? Just basic charge analysis, right? Okay, so you got a simple operator, 2-body operator. So where's all the complexity? Well, all the complexity is in the wave function, right? The wave function is an extremely high-dimensional, very, very complicated beast, right, that describes a system. I show here that it at least has 3n number of degrees of freedom, where n is the number of electrons. If we throw in spin, it goes up to 4n. Okay, so what does density functional theory do? Density functional theory provides an alternative to this by mapping the electron density, which is rho, I'm going to talk about that in a moment, to the ground state energy and properties, right? So we can get energy and properties as long as we have some function of rho. So now, why do we care about rho? Well, rho, which is here, is a highly integrated quantity. You take the wave function squared, and you integrate over all degrees of freedom except for 1. Okay, now you're left with, again, a very simple object that's 3-dimensional. It's experimentally observable, and much better to work with something like that, at least philosophically. So where does all the complexity go? All the complexity now goes to that exchange correlation potential, they call it, right? So the actual instructions for, if you gave me the electron density, what do I actually do to it to get an energy and properties? And of course, all that complexity is in the wave function is now moved here, and we don't know the form for this exchange correlation potential. However, as we do in science, often we try to build a hierarchy or a systematic approach for getting that unknown quantity. And again, this is a semi-systematic approach that doesn't have the sort of subtleties and beauties of the quantum chemistry hierarchy, but in the same breath, it's still worth thinking about. So at the lower rungs of density functional theory, you simply approximate FXC with model systems that you can solve. One is the homogeneous or uniform electron gas. You throw a bunch of electrons in a box with a background charge that cancels. You can actually solve that problem. Okay? That's the local density or local spin density approximation. Of course, this is not such a great approximation when you want to treat a molecule where you have divergent Coulomb potentials everywhere. The density is anything but homogeneous in a molecule. But stuff like LDA is quite good for things like metallic systems, where you have a much more uniform distribution of electrons. So in order to correct that and to climb up the ladder, you do a Taylor series expansion of the density to try and build in inhomogeneity. So the first step is to add in the gradient information. At least that's telling you how the density is changing. These are the so-called generalized gradient approximations, like PBE in physics or BLYP in chemistry. This is one of the most popular ones. And of course, you can keep going along those lines, adding in second derivative information to get the meta-GGAs, and so on and so forth. We take a slightly different approach and try to bypass that expansion. We stop at the GGA level in terms of our expansion in terms of rho, but that's actually not necessary. We could investigate functionals that build on here. I would say in general, the scheme that we're going to show you today is a general purpose scheme for doing any functional that adds what we call exact exchange. So the big problem with these, with density functional theory in general, is that an electron feels itself. It has what they call self-interaction error. And one way of alleviating or ameliorating that self-interaction error is to add in a little bit of the Hartree-Fokker exact exchange. And that brings you up to this level, which are the so-called hybrid functionals. Another big thing that they're missing is the sort of complete lack of non-local correlation, the sort of long-range van der Waals or dispersion interactions. So you probably should add those as well. I've done a lot of work in this area, but we won't talk about that today. We're going to talk about this correction here, which is moving into the hybrid functionals. Okay, so why is this a problem in the first place? Well, the problem really lies in the fact that we're dealing with periodic or condensed phase systems. So if one tries to evaluate this exact exchange energy, now a lot of equations here, but it's really not a big deal. This is the one to focus on, right? You gotta sum over all the orbitals and do a six-dimensional integral over space. This is like a Coulomb integral, only it's got the indices messed up, right? And that's what really this is the bane of our existence in exact exchange or any sort of same spin correlation methods, right? So instead of being I and I, orbital I and orbital I on electron 1 or on R, and orbital J and orbital J, it switches them. And that makes everything a lot more complicated. If it was the same indices, you could use things like fast multipole methods. You know, this is just a Hartree product. So in the condensed phase, what's usually done is you can look at this as a potential, right? If you form a pair density of orbital J and orbital I, that's just a charge distribution. And you can then consider integrating over that quantity and rewriting it as a potential, right? So it's sort of like if I had this charge density, what would a test charge feel, right? From that charge density. So we just rewrite it as a potential. And in order to do that in the condensed phase, you have to do a Fourier transform or a fast Fourier transform for each of these pairs. And then it's quite easy to evaluate. However, this requires, cubic computational effort because for each of these orbital pairs, you have to do an FFT. And now, traditionally speaking, that has led to a cost that was, an order or 2 orders of magnitude more expensive than a traditional GGA. Now, in that regard, I want to point out that there's been some tremendous progress in this area by the more than competent Jack DeSlip and Taylor Barnes and Paul Kent from Lawrence Berkeley National Labs and Oak Ridge, where they, I think, what do you guys got, a factor of 10 or so? Well, you'll tell us about that in the next talk. So these guys have went directly after the sort of reciprocal space formulation and have hammered this. So that's great. I'm going to show you a completely different alternative approach that's complementary in many regards to their approach. Now, so what we do is instead of really trying to deal with that in a proper parallel fashion, we sidestep it completely because we can take advantage of the fact that not all orbital pairs actually make an appreciable contribution to the exact exchange. So we take advantage of this natural sparsity and we do everything in real space. In order to do that, you have to transform the sort of canonical molecular orbitals, the sort of delocalized molecular orbitals, to a local representation. This is done by a unitary transformation that preserves the energy. And now, for all overlapping pairs of orbitals, right, we only have to consider the overlapping pairs of orbitals, we simply compute that same potential that we were talking about to get the energy with the Poisson equation in the short and intermediate ranges, and that's just subject to the boundary value, or the boundary values for that problem are just given by a converged multipolar expansion. So if you need the potential outside the area of orbital overlap, you just get it from a multipole expansion. So this offers you a approximation-free approach, as long as everything is done correctly, to calculating exact exchange. So we're not throwing things out, right? We're just dealing with them in a different way. So this allows you to compute everything with order and effort, and I'll show that to you in a moment. And however, that's, of course, would not be possible without the sort of generous resources from Argonne and the high-performance computing architectures that we have here. I'm going to talk to you a little bit about our accomplishments and what we've been doing at Mira to try and optimize the code there, and then show you what we've gotten done on KNL over the last 2 months. Again, we sort of standard hybrid MPI and OpenMP algorithm can now allow you to do hybrid density functional theory calculations sort of routinely on 10 to 100,000 processors, as long as you have the resources at your disposal. I think what you'll see here is something that I've been saying for quite some time now. If you decouple the exact exchange portion of the code from the rest of the stuff that you have to do in a DFT code, we now have flipped the problem on its head, and I think Jack and Taylor will tell you the same things, right? I think we're all now at the point where we're starting to flip the problem, and now the underlying GGA, the other stuff that needs to be done, the kinetic energy, the pseudopotentials, et cetera, now they're becoming the rate-limiting step, which is, I think, in some ways great, right? I think we just go back now and adjust that and fix those. So we have a significant cost reduction. So how do we do it? Let me give you some of the details before I talk about how we're performing on the KNL. Well, we do everything with a couple of knobs to make sure that you converge exactly to the exact exchange energy. So you have two different types of exchange calculations. You have an orbital with itself, and then you have an orbital with its neighbors, right? And we have to choose all the neighbors that are within a certain distance, and as long as we choose all the neighbors that overlap, we get the right answer, right? So you have to properly choose how many neighbors to include, and then you have to also properly choose a domain on which you solve the Poisson equation that completely contains the density, the orbital overlap. If you start making approximations there, you start making errors. So we have conservative choices for all of these, and we do everything on a sphere, right? So we have a Poisson equation radius and basically a distance cutoff for choosing pairs. Now again, just to hammer this point home, because I think, again, in many local electron correlation and local electronic structure theory methods, they're almost every single one of them are actually throwing out terms. We are not throwing out terms as long as, A, you are in a system that you can localize the orbitals. So if you're in a metallic system, we have to adjust the algorithm because there, the orbitals cannot be localized properly. And you are not gung-ho and crazy about the parameters, right? If you make the parameters really, really small to make the calculation really quick, you start making an error. However, if you choose the parameters correctly and they're completely reasonable, you rapidly converge to the exact answer. Okay, so again, more details as to how we do that. Well, we solve the Poisson equation on a subset, a spherical domain of the real space grid, right? And so what that requires is us to discretize the Laplacian. I'm showing you here a much more complicated form of this discretization because I'm just really happy about getting this done. We can now do any cell shape or grid, whether it's orthogonal, non-orthogonal. We can calculate now the exact exchange contribution to the pressure. So you can do isobaric, change the isobaric, isothermal ensemble. We have really the full functionality. At the end of the day, if you're in an orthogonal grid, all you need is the simple Jacobian transformation and a discretization of the Laplacian. This is something that we all know in this room, right? It's a standard stencil. We use a 6th order accuracy stencil. This is a 19-point stencil, so 3 points on each side in 3 dimensions. And we use a conjugate gradient method, and again, a spherical domain of the real space grid to solve each Poisson. So in other words, we have many, many small Poisson equations to solve. These Poisson equations are on a subset of the real space grid, and they're approximately 350,000 points each. That's the domain of the grid. So to keep it in mind, something like 70 points by 70 points by 70 points, again, for normal cutoffs in microcanonical NVE or NBT ensembles or energies or geometry optimizations. Now on Mira, this is the blue gene Q. What we do there is we don't MPI task parallelize. We do for each Poisson. We solve each Poisson using threading, right? OpenMP. And as you can see, this is for sort of energy type calculations or NVE ensembles. If you want to do NPT, isobaric, isothermal ensembles, you use a bigger grid. You see that we get nearly ideal. I mean, we're losing some threading efficiency up to about 16 threads. And after that, we still can take advantage of the hyper-threading. I'm going to talk more about this in a moment. So we're really happy about that. Of course, the situation changes a little bit on the KNL. And our overall strong and weak scaling, again, this is sort of for blue gene, just want to put the talk on, I guess give some reference to where we were starting. We have an algorithm where we choose the number of MPI ranks based off the number of bands. So a zeta equals 1, you have, for every orbital, you have 1 MPI rank, right? So for water 128, for example, you got 512 orbitals, you have 512 ranks if you're in the zeta equals 1. You can do less zeta or you could do more zeta, and these are usually exact multiples or divisors, right? So what's interesting here, again, I won't go into the detail because actually this is not the most up-to-date slide. I want to just give you the take-home message that we can do things like water 256 now, the exact exchange contribution in about 4 seconds. That puts you in the domain to where you can actually do ab initio molecular dynamics, which requires hundreds of thousands of repeated energy and force evaluations. This algorithm here that we're showing, like I said, is a little bit old. We have introduced a very efficient static load balancing algorithm coupled with asynchronous communication, and we've completely made this computation bound. Our original algorithm was much more communication bound. So that's why we're focusing for the rest of the talk on the computational aspects of this problem. And again, just to drive this point home, and again, I think Taylor and Jack will sort of give you the same picture. I don't know their crossover and whatnot, but you see here that the exact exchange, if I use the zeta equals 4 algorithm, that would be something like 64,000 cores for water 256. You see that now the exact exchange is about 4 to 5 times cheaper than the GGA. And that crossover, if you're using, in the strong scaling regime of the exact exchange algorithm, can happen even as soon as something like water 64. So, I mean, that's, I think it's good news and bad news. One slide about an application to show that there is some science that you can get out of this. If you try to model the structure of ambient liquid water, this is extremely challenging. If you use GGAs, you see that it's completely overstructured and not anywhere near the right liquid structure. There's all types of wrong properties. For example, in a GGA DFT world, ice will sink in water, right? So in order to get semi-quantitative or quantitative accuracy in the radial distribution function and a correct recovery of the equilibrium density, we're actually getting it to within 1%. You really need to go beyond the standard GGAs, right? Van der Waals plays or non-bonded interactions play a key role, as well as exact exchange. Okay, so now KNL. What is the first thing we did? And you might think, I mean, again, I think in some ways this is a crazy idea. In some ways it completely makes sense, right? So the first thing we do is we make the problem a lot harder, okay? The first thing we do is we say, forget this spherical domain, right? We move to a cubic domain, right? And now that has disadvantages and advantages, and I'm going to show you for the rest of the talk that the advantages of this approach outweigh the disadvantages by an order of magnitude at the very least. So disadvantages. A sphere, and again, the radius of the sphere would be the same as half the side length of the cube, right? So no cheating or fooling around. We essentially double the number of points, right? It's a factor of 6 over pi from the volume ratio, the ratio of the volume of a cube to the volume of a sphere, right? We've got twice as many points. Okay. Well, twice as many points means more memory. Twice as many points means more computation. And if you're doing something like an iterative procedure like conjugate gradient, where it depends on the number of points, we even have more CG iterations. So more CG iterations, more points, more memory, more time per iteration, blah, 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 blah. Okay, so now, what are the advantages? Just conceptually speaking now, and then I'll show you why they are advantages. Well, now we have a unit stride and sequential memory access domain, right? This is key, as you've seen from many, many talks this week, for KNL, right? This is key for vectorization. In order to figure out, when you're doing that Laplacian, in order to figure out who's my neighbor here and who's my neighbor there on a spherical domain is non-trivial and requires, 1D to 3D mapping back and forth. We wrote it the best way we can, and you will see that really just causes a lot of memory operations, a lot of cache misses, tremendous problems. It also requires logic. You got to know when you're at the end of the spherical domain. With a cube, you don't need any of that. We properly pad now and get rid of all logical operations, right? So unit stride, sequential memory access, get rid of all the logic, right? That allows for better vectorization. We're now unrolling every loop by hand. And I guess on top of that, we could say we get a more accurate energy and potential because we're considering more of the problem explicitly with the Poisson equation. However, we really don't need that. We were converged already. But I guess it's an extra bonus. We're not going to throw it out, right? OK, so now, and again, I'm going to take you through this sort of step by step. I'm giving more data points here than I'm going to discuss. Let's talk about the single thread efficiency first. All right, so we have blue gene Q. Let's look at single thread. This is sphere and KNL in red. This is the spherical domain with the CG and the cubic domain with the CG, right? These are two different algorithms, though. This one has been completely optimized for the cube. This one has been completely optimized for the sphere. So again, despite a significant increase in the number of grid points, right? It's going up by a factor of 6 over pi, approximately 2. And the number of CG iterations, which are going up for these problem-sized domains about 30% more iterations, you see already that we observe substantial savings, right? Now, on the blue gene, right? Let's go back to blue gene, right? On the blue gene, we have been doing everything wrong all along, apparently, right? We should have been actually doing the cube, right? Right? Once we optimized the code and really stared at this and took all this into account, unrolling everything, we actually see a speed up of 1.4 on the blue gene, right? The only problem is, of course, again, right, you have to now hold the cube as opposed to the sphere, so it's a little bit more memory, but these are not big memory, right? 350,000 points, these are a few megabytes just to hold the problem. So we're not talking about big memory here, and that, of course, is going to play a key role. On the KNL, we go from 4.24 seconds to 1.83 seconds, so we have a 2.3x speed up, and again, that's because of our efficient vectorization, unrolling all the loops, no logic, unit stride. We have our own customized way of doing this stencil, right? We're touching every single line of code. And I don't think we've used half the tricks that are available to us yet. Overall then, now if I consider, let's forget the sphere now. Let's think about the cube. So if I'm going to really do a fair comparison here. I'm not, this is not snake oil. Let's compare the cube on the optimized cube on the blue gene to the optimized cube on the on KNL. You see a speed up of approximately 3. So that's step 1. We get a computational speed up of 3. And again, I just, in terms of the roofline model, right, we're dealing with, right, so in some sense, we have gotten rid of high arithmetic intensity operations. We have no matrix-matrix multiplications. What is happening in this solution are dot products, Daxby, right, adding 2 vectors with a constant in front of one, or a scalar multiplication, and we have a sparse matrix vector multiplication when we apply the stencil. So we got rid of all the high arithmetic intensity operations. Of course, we got to do a ton less, but that presents challenges when you're trying to use the KNL efficiently. OK, so what was our next step? Now, this slide I'm actually really, really, really happy with. And I think it's something that affects much more than exact exchange. We're in the process of writing this up right now and formalizing it. But we believe that we have discovered the most efficient preconditioner for elliptical boundary value problems like the Laplace equation, the Poisson equation, Poisson-Boltzmann. Francois, you don't believe it? I'm only kidding. You made a face. If you look at the incomplete Cholesky factorization scheme, this is some of the most efficient ways of doing the Poisson equation. This is no preconditioner. This is symmetric, successive symmetric over relaxation. Here's your standard incomplete Cholesky factorization. So here what you're doing is you're writing your matrix, this is the stencil, as an approximate Cholesky decomposition, right? So a lower triangular matrix times itself. Only now we enforce that that lower triangular matrix has the same sparsity as the original matrix, right? That's the incomplete Cholesky factorization protocol. There are ways, of course, so you're discarding all the off-diagonal information or the off-band information. There are ways of introducing that information back. This makes the modified incomplete Cholesky factorization scheme. And what we have done after that is another trick where we sort of smooth or symmetrize this modified incomplete Cholesky factorization, right, by exploiting the symmetry and sparsity of the stencil, right? Now, what's interesting is that if you look at now this is a factor of the problem set size, this is a 1,000,000-point Poisson. You see that we are doing much better than any of the other preconditioners, and this is a much lower slope line, right? So this continues on. The biggest we have right now is about 150 on a side, and we are still significantly better in terms of number of iterations than any other preconditioner. We don't know how long that will last, so we don't know that this would be an appropriate approach for solving, a 10 billion point Poisson or 10 billion point Poisson-Boltzmann size, but definitely over a tremendous amount of sizes that affect many areas of computational science. That's only the first benefit. The other benefit is that it has a tremendously low memory overhead. In typical incomplete Cholesky factorizations, you will need to store that preconditioner. We have a way of solving that preconditioner on the fly, so we don't actually have to store the matrix. That allows us to have just a slightly additional memory overhead of about 20–25%, which in our case is a couple of megabytes. The fact that we don't actually have to go through and form the preconditioner, and we have an algorithm for doing so, that's sort of a closed form analytical expression, saves tremendously on the computational overhead. These are all, great facts, and we don't fail because of pivoting issues as we get larger. The benefits seem tremendous. Okay, so now what happens if we introduce the preconditioned conjugate gradient algorithm? Okay, so again, same thing. Now we're going to reference the cubic domain with our optimized CG algorithm, and now we're going to so that's our reference point. Now we're doing the cubic domain, so same domain, but with our preconditioner. Okay, so as you go from the conjugate gradient to the preconditioned conjugate gradient, we're observing tremendous speedups, another 3.5 factor on the blue gene, and a factor of 2.5 on the KNL. Now, this is the result of two competitive features. On one hand, we have the savings in the number of iterations that we just mentioned, right? So we are saving about a factor of 8 in the number of iterations. So an unpreconditioned or non-preconditioned problem takes about 250 iterations, and we have reduced that to about 10, right? Sorry, to about 30, right? So we have a nice solid factor of 8 there. And I have to say that this is all from a zero guess. So we're not even using a guess for the Poisson solution. Our preliminary calculations over the last night or two shows that if we use any intelligent guess here, which of course is subject to further optimization, we're seeing that this number goes down by another factor of 2. So I think conservatively speaking, we're probably going to get another factor of 2 here just from using a guess. That's appropriate. All this is using is a zero guess, right? So just put 0 as the potential, just to make it more fair in the comparison. Okay, so that's a tremendous savings of about an order of magnitude increase in computational savings or speed up. However, when you do the preconditioned conjugate gradient, each iteration takes a lot more time. Now, of course, our special preconditioner here deals with that in a very, very efficient manner because we get rid of the overhead, and all we're left with is a data-dependent forward and backward substitution, which we are working on optimizing. All of it's unrolled at the moment, but we think we can do better, right? So on Blue Gene, it's about 130% more to do per iteration, but then you save a factor of 8 in the number of iterations. KNL, it's a 200% increase. And again, that's because of data dependency and the forward and backward substitution, right, which we need to work harder on to take advantage of vectorizing that code a little bit better. So I think we'll get some there as well. So overall now, if we compare the cubic domain preconditioned conjugate gradient to the, from Blue Gene Q to KNL, we get another factor of 2, right? So we got a factor of 3 moving from spherical to cubic, and from CG to PCG, so preconditioning gets us another factor of 2. Okay, so just closing up here, two or three more slides. What about threading efficiency, right? So that was all good news. Here's some bad news, but I think we have a solution that sort of directly addresses it. On the blue gene, you see, again, now let's just solve one Poisson equation by threading over a given node, right? So dashed lines are ideal. The blue gene Q, you see a very, very decent, I don't know if this is ideal per se, but it's very, very efficient, very, very high threading efficiency. And again, why is that the case? I think we understand that now, right? You have the crossbar, which allows you to access a fairly large L2. Our problem completely fits inside of L2 cache here. And it's that simple, right? So, you know, the threads, they have access to the parts of the memory that they need in a much more efficient way, right? And in the KNL, that's just simply not the case. So we start losing a bit more on the KNL. However, right, we feel like, you know, well, why do we have to, you know, use all the threads on a node to solve one Poisson? We have thousands, hundreds of thousands of Poissons. Why not solve a couple of them on a given node at the same time, right? And we would argue there that, and that would allow us to get, you know, more efficiency here. Maybe we use 2 or 4, right, instead of losing more and more. Okay, so of course that is especially possible on a KNL because of the high bandwidth memory, right? So if you look here at the making the problem larger and larger, if we look at the time to solution, if you just use the DDR versus the time to solution, if you just use MCD, this is in flat mode, right? You see that once the presence of MCD really significantly boosts the performance of the algorithm once you can no longer fit inside of L2 cache. So our problem fits inside of L2 cache for a single Poisson. Once your problem gets too big, about right here is where the L2 cache limit is. Now, of course, MCD-RAM is giving you a big speed up. So again, it's the fact that MCD-RAM is present on the KNL that's going to allow us to do this solution, right, of solving simultaneously multiple Poisson equations. Now, we weren't sure we were able to get this, so we stayed up till over 3 a.m. last night to get this plot. But we didn't want to just show that because we can actually show you how many Poissons we can solve on a node. It just took us a long time to get there. I would argue also we have only had access to the KNL for a couple of months now when my graduate student Jun Ting came to Argonne for an internship this summer. So if you take that seriously now and try to solve this number of simultaneous Poisson equations, or this number of Poisson equations simultaneously, just using the DDR versus MCD, you see 2 different behaviors. And we haven't done any hyperthreading study yet. You see that there's a sweet spot actually with DDR, right? So in DDR, you kind of want to do, I don't know, between 2 and 4 Poissons at the same time. And again, right, I would argue that this is, again, 2 competing effects, right? You have the threading efficiency on one hand, right? Less threads, more efficient. And then you have, again, this effective L2 cache. As you put more and more Poisson problems, they simply can't fit in L2 anymore, and they either have to go to DDR or MCD. And when they go to MCD, the benefit is tremendous. And when they go to DDR, you better keep it small, right? So again, right, this high bandwidth memory gives us the opportunity to achieve a higher effective threading efficiency if we just solve simultaneously many Poisson equations. So last slide, and then conclusion, sorry. So okay, once the dust settles, right, I mean, I've compared what I would argue fairly every step of the way. Okay, so now if we go back and say, we started with the sphere in CG on blue gene. That's here, single thread, right? We have a new algorithm, right, that takes into account the fact that we solve everything on a cubic domain. We make everything bigger and harder. However, it's vectorizable. It's got unit stride, sequential memory access, better vectorization properties. We hit it with this state-of-the-art preconditioner, reduce the number of iterations by a tremendous amount. At the end of that day, and with the hardware available through KNL, we are getting a clear order of magnitude, right? That's simple. And I think I'll leave it at that, right? Because I'm over time. But thank you.
Well, perhaps in the name of time, if you have questions, you'll be around today.
I'll be around for the rest of the conference.
Okay, thanks.
Thank you. Yeah, sorry for going over.
Problem is interesting. Very interesting.
Thanks.